All right, so we are hopefully at this point starting to appreciate why we need nonlinear devices. We saw ideal diode as a device that already can do something useful to us. We used it to measure the strength of a signal. That's something you cannot really do with just linear components. And there's tons of other applications for these ideal diodes. Now, the name says it, right? If it is an ideal diode, if it is an ideal something, it means that it doesn't exist. And what we need to do is to come up or find a device that in practice can do most of those functions for us with slight deviations from what we expected from the ideal device. And the dominant device in this case is a semiconductor p-n junction. We'll see that if you form a p-n junction from a semiconducting material, it behaves in a way that resembles an ideal diode in most cases, and in vast majority of the cases you can actually use it instead of an ideal diode and do the function that you were hoping to do with the ideal diode. So how do we make a p-n junction? Well, a quick review or overview. We know that electrically you can put materials in three categories. There are insulators that do not conduct electricity. Basically, the material structure is such that you don't have free electrons to carry electrical charge from one end of a, let's say, potential source to the other end, right? So if you apply voltage difference between the two ends of a piece of these materials, there are no free electrons to move from the one end of the material to the other end, and therefore there is no current. They are insulators. They have very, very large resistances, electrical resistances. At the other end of the spectrum, you have conductors, and good ones are metals, for example. And in metals or in good conductors, you have a lot of free electrons. Free electrons means electrons that are moving around freely in the structure of the material. They are not bound to any particular atom or molecule in that structure, and they can hop from one atom or molecule to another with almost zero extra energy, right? So you have, they call it a sea of electrons in case of metals. You have a lot of electrons that are available that are just moving randomly in the structure. As soon as you apply a potential difference between the two ends of these conductors, the electrons will travel towards the, for example, positive, more positive voltage, right? And then in between these two extremes, you have semiconductors. These are materials that are neither good conductors, that you can use them, for example, to make wires from them and things like that. And they are not insulators. You cannot use them as dielectrics. They're somewhere in between. So let's say if the resistivities of insulating materials are 10 to the 4, 10 to the 5, 10 to the 6 ohm centimeter, or higher, or the resistivities of metals is on the order of milliohm centimeters, or maybe even lower. Semiconductors are somewhere in between. They're, let's say, between 0.1 ohms to maybe 100 ohm centimeter. That's the range of resistivities you get for semiconductors in typical applications. Why do we like semiconductors? Well, that is the reason. We can change the resistivity very precisely and set it to where we want it to be. You know, unlike for metals. For metals, if you have a piece of gold, for example, there's not much you can do to change the resistivity of that piece of gold in terms of processing. If you have a piece of glass, there's not much you can do to make it electrically conductive. But with the semiconductor, we have come up with some processing techniques to play with that resistivity quite a bit. And by doing that, I mean we have come up with ways to change the number of free electrons or charge carriers in a piece of semiconductor. So here we have a schematic, a 2D drawing for crystalline silicon. Well, of course, it's not that simple. This is a simplification. It's a 3D structure, but on a piece of paper, you can show it as this. Silicon is from the 4th group in periodic table, meaning that it has 4 electrons moving around the nucleus in its outmost energy band. And again, from basic chemistry, we know that these, let's say, atoms that are not noble gases, they want to complete their outmost bonds in terms of the number of electrons so that they look like a noble gas. And in terms of, let's say, silicon in this case, it has 4 electrons in its outermost band. It needs 4 extra electrons to basically look like, I think it is neon, the next, or I may be wrong, but anyway, to make it look like the next noble gas in the periodic table. So it needs to have 4 electrons there, right? What it does in a network like this, in a lattice like this, is that it contributes its 4 outermost electrons, shares them with 4 neighbor silicon atoms. So the silicon atom here, each one of them is sharing 4 electrons, contributing their 4 and sharing 4 electrons from their 4 neighbor atoms. Each one of them is having 8 electrons in its outermost shell. This is a covalent bond. It's a very strong bond, chemical bond. And under normal circumstances, at 0 Kelvin, everybody is happy here. They all see 8 electrons in their outermost band, and they all are happy. Now, at 0 Kelvin, therefore, you will not have any conduction through this material. If you apply a voltage difference between the two ends of this piece of material, there are no free electrons to carry charges for you, right? So it behaves like an insulator. As soon as you raise the temperature to, let's say, a few degrees Kelvin, or maybe a few tens of degrees Kelvin, you will have enough thermal energy that from time to time, one of these bonds gets broken. So this bond gets broken, and as soon as that bond gets broken, the electron that was shared between these 2 silicon atoms is now able to move, right? So it can hop over here, but remember, this silicon is happy. It doesn't need it, right? So it doesn't really make a strong bond to any of those silicons. Or it can go over here, or it can go over here, right? So it can start moving around in the lattice. Of course, and again, this is a very simplified version of what is happening in a real semiconductor. You know, we are dealing with classical demonstrations, but in real life it's quantum based. But anyway, you have that electron that is moving around. But in its place, between these 2 silicon atoms, what there used to be a bond where there used to be an electron, now you have an empty place for a bond. Let's just call it a hole. So where you had an electron, now you have a hole, right? A missing electron. And interestingly enough, this hole can also move. What can now happen is that this bond here can break. The electron that is produced over there can jump over here, form this bond or reestablish that bond. Now it's as if your hole has moved to that place. And then this bond can break, for example, right? And the electron that was here can jump over here, reestablish this bond, but you have a hole that has moved in that other direction. But it's a missing electron. So it's when this hole is moving in this lattice, it's as if a positive charge is moving in lattice. The electron, as it is moving around, it's a negative charge. It's an electron, right? It can move around. But this hole, it's a missing electron. So it was charge neutral before. Now you're missing an electron, and this missing electron is moving around. So it's as if you have a positive charge carrier. If I apply a potential to the ends of this material, let's say positive here, negative here. Now the hole is a positive charge carrier. It's representing the missing electron. It will be repelled by the positive charge, so the hole will start to move in that direction. The electron, on the other way, will be moving towards the positive electrode. And now what you have is basically charge carriers. You can start to have a flow of electricity through this piece of material. You know, electrons and holes will do the charge transport for you. So in semiconductor physics, we actually look at a hole as a charge carrier in its own right? So we look at it as if we have a positive charge carrier in the lattice that is responding to input voltages and fields the opposite way that an electron does, right? So, of course, it is not a real charge carrier, right? It's a missing electron. So therefore, you know, if you look at this electron, it can jump from silicon to silicon relatively easily, and it is not bound by anything. The hole is not as free to move. You know, first of all, some bond somewhere has to break that is fairly close to it, and then the electron moves to the empty spot that you had here, and you have an empty spot in the new spot, in the new location. So it's not as agile as your electron in a silicon lattice, at least, right? So it's as if it's a heavier piece. You know, it's going to behave a little bit differently than an electron in a lattice. And that is actually the foundation or the reason behind the difference in behavior of, let's say, N-type transistors and P-type transistors that we will talk about later. In silicon, electrons move a bit faster than holes. Now, so far this is an intrinsic piece of material. You know, all the charge carriers are produced from broken bonds of silicon atoms and so on and so forth. Nothing really that interesting. For the most part, this is behaving as a bad conductor, right? So you raise the temperature to a few hundred degrees Kelvin, you know, room temperature and things like that. Still not a very good conductor, right? It's conducting, but not that much. The number of those electrons is really, really small. The electrons that free themselves from those bonds. Now, let's do an experiment here. What we're going to do is that we're going to get this silicon here, take it out, and replace it with phosphorus. So I remove one silicon from this lattice and put a phosphorus atom in its place. Now, phosphorus is from the 5th group in your periodic table. It has 5 electrons in its outmost bond. And to look like a noble gas, it needs 3 more. It needs to have 8, right? So what happens is that once you put it in this lattice here, it creates a bond with 4 silicon atoms that are in its neighborhood. It has 1 electron here that it doesn't really like anymore, right? Now it has satisfied, you know, its, let's say, desire to look like a noble gas. It has shared electrons with 4 neighbor atoms. It contributed 4. There are 4 neighbor silicons. It has 8 in its outmost bond. It's not really strongly attached to that extra electron that it has. It actually wouldn't mind getting rid of it if it could. So as soon as you provide a little bit of extra energy, what happens is that this electron is detached from the phosphorus atom. What you have left is a phosphorus, a positively charged electron, but an electron now that can move in the lattice relatively freely, right? So it can jump from here to here. None of those silicon atoms have to be ionized now. You have an ionized donor. So phosphorus has donated an electron which is a negative charge. So we call it an N-type, N for negative, dopant. There are other atoms that we can use. For example, arsenic would do the same thing here. But P, phosphorus, is the more common dopant. So by putting 1 phosphorus atom here, I actually added 1 charge carrier to the lattice. I can do something else. I can go and, let's say, take one of these other atoms here and replace that guy with, let's say, boron. Now, boron is from the 3rd group in periodic table. It has 3 electrons in its outmost bonds. And because of that, when you put it in here and you give it 4 electrons from the silicon atoms in its neighborhood, it had 3 of its own. It still has 7. It's not 8. It's not like a noble gas anymore. So what it does is that it goes and brings in an extra electron towards itself so that it feels happy. And now it has 8 electrons in its outmost bond. But where does that electron come from? Where does the electron to satisfy this boron come from? It actually comes from one of those broken bonds, right? So by having a boron in its in your lattice, what you're creating is an extra hole. Each boron atom gives you one hole, contributes one hole to the lattice. And as we just talked, holes behave the same as electrons for the most part in terms of being able to carry charges to respond to electric fields. So now you have a type of a dopant here that is contributing a hole to the lattice. So B boron accepted an electron from the lattice, or you can say donated a hole to the lattice. Holes are positive charge carriers. So we call dopants that behave like boron p-type dopants. Right? So the short version of this story, in a silicon crystal, initially you don't have too many electrons, too many charge carriers, but by choosing proper atoms and replacing some of the silicon atoms in your crystal with those atoms, you can actually increase the number of charge carriers in your crystal. If you choose the N-type dopants, you increase the number of negative charge carriers in your piece of semiconductor. If you add P-type dopants like boron, for example, you increase the number of positive charge carriers or holes in your lattice. And let's say if I want to reduce the resistivity of this piece of silicon, I can add as much phosphorus as needed. By dropping the number of increasing the number of free electrons, I drop the resistance. I could do the same thing with boron, right? So I could add enough boron there so that I have so many holes that will meet the requirement for the electrical resistivity. I shouldn't do both at the same time. So let's say if I add one boron and one phosphorus to the atom, to the lattice, well, the hole that boron donates to the lattice is going to cancel the electron that phosphorus is adding, right? The electron and hole, when they meet each other, remember, going back to the original silicon lattice, where did the electron and hole concept come from? You had an electron that left its place in the lattice. So you had an electron that left and a hole that may be moving in a different direction. If it is a random movement, the electron and hole may meet. And in this case, we say it's a recombination. So in one case, you have generation of electrons and holes, but you can also have recombination. If the electron and hole that were generated initially come back and meet each other, well, you will have the bond back, and you basically lose both the electron and hole. Now, if you do the same thing here by adding one boron and one phosphorus, you donate one hole and one electron to the lattice, they can still meet and actually cancel each other. They can recombine. And in this case, your net resistance doesn't really change. Net resistivity doesn't change. So I usually use one or the other, right? I use N-type dopants to reduce my resistivity, or I use P-type dopants to reduce the resistivity. I don't usually use both at the same time. However, something really interesting happens when I go and then, okay, so one more thing. If I have more N-type dopants in a piece of silicon than P-type, or if I only have N-type, I call that piece of silicon to be N-type or N-doped. If I have more P-type dopants, I call that piece of silicon P-doped or P-type. Now, the interesting thing happens, and so far you only have a resistor, right? Either P-type or N-type, but it's a resistor, and it behaves like a resistor. An interesting thing happens when I bring a P-type silicon, piece of silicon, and put it really, really close to an N-type piece of silicon. So in this case, for example, let's say I had a configuration like this. So a border between the P side and N side. So let's say I have, let's say P-type silicon on the left side so that it is consistent with your slides. An N-type silicon on your right side. right? So it is silicon. I have, let's say, phosphorus on the right half of this piece and boron on the negative side, or on left side of this piece of material. Now something super interesting happens right away. So what happens on the N side is that I know I have extra electrons here. I know I have electrons that can move about, and those contribute to charge conduction. They are loosely connected to the lattice. On the P side, I have holes that again are moving around. I have extra concentration of holes on the P side. And these holes, like electrons, randomly move around as long as you don't have an electric field applied to this thing. Now, so I have over a high concentration of electrons on the next side, the right side, a high concentration of holes on the left side. And I keep in mind that for every electron that I have here, I have an ionized phosphorus atom, for example. And for every hole that I have here, I have an ionized boron atom, right? That hole came from a boron. When the positive charge carrier starts to move in the network, my boron here, that is fixed in its place and cannot move, will have a negative charge. It is ionized. Same thing with the phosphorus. Once it donates the electron to the network, it stays in its place, and oh no, I have an ion. It's a positively charged ion, right? So for every electron in the network, I have a positively charged ion. For every N-type dopant, for every hole, I have a negatively charged P-type dopant. When you bring these two materials very close to each other, what happens is that, diffusion. When you have a high concentration of something at some location, a low concentration at some other location, and these things are free to move, even randomly, they start to migrate towards the place with lower concentration. And we are all familiar with this, right? So if you have somebody smoking in a room, at the other end of the room, sooner or later you're going to smell the smoke or perfume. Or if you put a piece of sugar in water, after a while, the high concentration of sugar molecules will basically, around the sugar, the cube of sugar, are going to basically move towards the entire, let's say, glass, and the entire water will taste sweet, right? So this is a process that we are very well familiar with. And then when you bring a P-type and N-type of semiconductor close to each other, well, that's what will happen. You have a high concentration of electrons on the left side. On the right side, these guys will migrate to the left side, right? And the opposite happens to the holes. The holes will migrate to the right side. Okay? And there has to be an equal number of them at the end of the story. Now, this happens right close to the border. This is where the two sides are seeing each other. If you go deep on either left side or right side, those regions will not know that something has happened at the interface between these two layers. So after a while, once this migration happens, at this border between them, all the electrons and holes that you had, let's say the electrons and holes in this region, all the electrons that you had here have migrated to the left side. Now what happens to an electron that goes to the P side? Well, the electron, you have an abundance of electrons here. They go to the P side. In the P side, you have a deficiency of electrons. You basically have a lot of holes. So one of those electrons and one of those holes will meet, will recombine, and the electron basically disappears. But what has happened here is that over here, when the electron left this area, you had a positive ionized ion, right? A positive P-type dopant. Same thing on the left side. Once the holes migrate to the right side, each hole leaves behind a negative charge, ion, in the lattice that is fixed in its place. It cannot move, right? It has lost the hole to the recombination on the right side. So after a while, you have this ionization. You only have these ionized dopants left close to the border. And all the electrons and holes will travel to the left and right. But now look at what happens now. Now let's assume that this electron wants to move to the P side. It is still trying to continue with the diffusion process. The electric field direction, so once you have a separation of charges here, more positive charges on the right side, negative charges on the left side, and these are fixed, these cannot move. You develop an internal electric field that is pointing in this direction. Okay? Maybe let me talk about the hole for now. So what the direction of the field means is that if you put a mobile charge that can move around, it will move in the direction of the electric field. You know, the same as applying a potential difference between the two ends of a piece of material. Now, with that electric field generated internally, automatically, because of the diffusion of these extra charge carriers, if a hole is close to this border and wants to move to the N side, now it has to overcome this strong electric field, because the electric field is pushing the positive charges to the P side. The hole, if it wants to go over this region and reaches the N side, it has to overcome this barrier. It has to have enough energy to jump over this region. Notice this region is depleted of charge carriers. You know, all the electrons that I had here, they already have diffused into the P side, and they left behind their dopant ions, and same thing with the holes. This region is depleted of charge carriers. I call it depletion region. And once you have this depletion region formed, which happens automatically, holes cannot travel from the P side to the N side. Same thing about electrons. If an electron wants to move to the P side now, it has to overcome this electric field. Remember, electrons would like to move in opposite direction to the electric field. You know, they're negative charge carriers. So if the electric field is pointing that way, the electron wants to move in the opposite direction, or it is pushing the electrons in the opposite direction. And for this electron to end up on the P side, it has to overcome that barrier. And that barrier is a potential barrier, right? It's an energy barrier. It has to gain a little bit of extra energy in order to go over that bump. And over time, after a short while, this process becomes stable, meaning that the field that you produced here becomes strong enough that it stops the movement of charge carriers from each side to the other. The electrons cannot move from N side to the P side, holes cannot move from the P side to the N side, and everything is under equilibrium on either one of those ends. Now, so with this structure, we call it a PN junction, right? So you have a piece of P material connected to a piece of N material. Now, with this, let's see what happens if we go and apply a potential here to this material. So from outside, let's assume that I go and apply a more positive voltage to the N side. Let's just call this V bias. A more positive voltage to the N side than the P side. So Vn is larger than Vp, right? Something like that. Let's say I apply 2-3 volts of external voltage to the N side than the P side. So if I apply a voltage in this configuration, you know that, you know, if within a conductor or semiconductor or even an insulator, you're going to create a field between this end to this end. The value of this field is proportional to the voltage difference, properties of and maybe dimensions of the piece of material, right? So you're creating an external field here. So let's just So this is my PN junction. Right? I'm just going to put the name here. So your external DC source produces a field that is again in the same direction as internal electric field. So let's just call it this E internal, and you have E external. E external and E internal are in the same direction. It's a field. It has direction as well as value. If they're in the same direction, the total field is the sum of these two, E internal and E external. So you have a larger field that is across the depletion region. Actually, what happens is that by doing so, you make this depletion region a little bit larger, right? So it becomes a little bit larger, you extend it to both sides. And what you're doing to the charge carriers is that you're actually making it even more difficult now for them to go from one side to the other, right? So if this electron wanted to move from the N side to the P side, previously they had to overcome field E or E internal. Now they have to overcome E internal plus E external. So it has actually become even more difficult for them. So you do not really expect to see much current. If I call this I, let's just call it ID. So if you apply a more negative voltage to the N side, more positive voltage to the N side than the P side, you do not expect much to happen. You do not expect to see a lot of current here. There will be a little bit of current because of the random generation of electrons and holes here, right? And that's just a tiny, tiny amount of current. But let's do the opposite. Let's switch the direction of this so that in this case, I apply a more positive voltage to the P side than the N side. So Vp is now larger than Vn. And if this is the case, then what does it happen? What does it do to the internal field? The external field is now in this direction. Okay? And when you look at the total field, the internal field now has something taken away from it. E external is compensating for some of that E internal. What happens is that then the depletion region becomes actually a bit narrower. We are not worried too much about that. But the consequence is that now electrons do not need as much energy as before to jump over this barrier. They still want to diffuse into the P side, remember, right? Now you basically reduced the barrier height for them. You made it easier for them to go over that. And the larger this V bias is, the easier it will become for the electrons on the inside to move to the P side or holes on the P side to move to the N side. So you're making it easier for these guys to continue the diffusion that they love to do. As it turned out, the relationship between the voltage that you're applying and the current, basically the movement of the electrons and holes, is exponential. So if you go and do the math, I'm going to rename this VD to VD, V bias to VD. I'm going to point this as ID, choose this as ID, and let me get rid of these. This is going to behave like a PN junction. So for a semiconductor PN junction, the P side is your anode and the N side is your cathode. Now, if you look at this, if you take this notation for ID, VD, and all those things that we talked about, the ideal diode before, you can show that for a semiconductor PN junction, ID is some value of IS times e to the power of VD, the voltage drop across the diode, as per our convention, right? Divided by NVT minus 1. So let's focus for 1 second on the relationship between ID and VD, then I'll talk about those other variables. VD and ID are now exponentially proportional to each other. How? If VD is positive, you can see that this term is going to grow exponentially. Very quickly, it just becomes much, much larger than 1, and it's going to depend. You know, ID and VD will have an exponential relationship. If VD is negative, what happens is that this term for a large enough VD, this term will actually becomes negligible, and you only have a current in the reverse direction that is IS, right? So now, what are these variables here? ID and VD we already know. IS is called the saturation current of the diode. It's a property of the diode. The way that we make it and the dimensions of the diode will set the value for IS. Typical values are somewhere in the range of, let's say, milliamp for really, really large power diodes in power electronics, to femtoamps and smaller for diodes that are integrated on chip. Typical values for diodes that you buy from a supplier is on the order of nanoamp to picoamp range. So IS is the saturation current for the diode. And for the typical values, I'm going to say 1 picoamp to maybe 1 microamp. This is the common range, right? But as I said, you can just push it all the way to femtoamps and autoamps, or maybe milliamps if you have a really, really big diode. It is proportional to the size of the device. Where does it come from? Well, remember this random generation of electrons and holes here that we said, it just happens. Temperature, thermal energy break some of those bonds from time to time, and as soon as that happens, if you produce an electron hole pair here, the hole is thrown to the P side, electron is thrown to the N side, so there is a little bit of current that flows in that direction. But it's a very, very small current. So that's IS, that's the saturation current. VT is thermal voltage. And its value is found from here, kBT over Q. Kb is the Boltzmann constant, T is temperature in absolute degrees, temperature in Kelvin, and Q is the charge of an electron. At room temperature, so this is a temperature dependent value, right? So the higher the temperature, the higher the thermal voltage. At room temperature, Vt is about 25 millivolts. It's actually closer to 26 millivolts, but just to make our lives a bit easier, we're going to use 25 millivolts for our calculations. If you need that extra millivolt in your calculations, you can do it with a computer or with a calculator if you don't mind. But 25 millivolts is a nice number, right? So 1 over 25 millivolts is 40. If I have anything divided by Vt, I can just multiply it by 40 and then move on. So Vt is a thermal voltage. It comes from the quantum mechanical behavior of this device. And then N is the ideality factor. And this is a deviation from an ideal semiconductor PN junction. The device that I showed up here is an ideal semiconductor. The interface between the P side and N side is really abrupt. You have P side on one side, N side on the other side. The dopant concentration is constant, all those things. This is again ideal. In a real world, the dopant concentrations will move from being N to P. There is a little bit of transition. So this N represents that. And typical values are from 1 to 2. The closer the diode behaves to an ideal diode, the closer that value will be to 1. Right? So for integrated diodes, the value is close to 1. For discrete devices that you use in the lab, it could be around 2, 1.5 to 2. So these are the three values. These are properties of the diode. You have to get them from the manufacturer of the diode, or sometimes you may be able to measure them. IS, Vt is the thermal voltage. We usually assume room temperature operation. And N is again given by the manufacturer. Once you have those numbers, ID, VD relationship is as shown here. Now, what are the values? What kind of values we're talking about? So, for example, if let's just use some numbers here. Let's just try to see how the device behaves as I change ID and VD. Let's look at the ID-VD characteristic curve for a semiconducting PN junction, right? So I have some values here that I'm going to use. Again, this is from your slides. So let's assume for this device, for this particular device, IS is 1 picoamp, and N is 1. 1 picoamp means that, it's not a big device, but not a small device, something that you can buy off the shelf and use. N of 1, just so that our calculations are a little bit easier. And let's just plug in some numbers here. So let's use a VD of -1, for example, to begin the work. And I have this expression to calculate the current for a given value of input voltage, IS e to the VD over NVT minus 1. So for any value of VD, I'm going to calculate the value of ID from that expression. If VD is -1, well, N is 1, VT is 25 millivolts, so I will have, for this expression here, I will have e to the minus 40, which is practically 0, minus 1. So for VD minus 1, it turns out that ID will be minus IS, or minus 1 picoamp, approximately, right? But very good approximation. If you go and do this for minus 0.5, again you will see that ID is very much close to minus 1 picoamp, right? So e to the minus 20 and e to the minus 40, both of them are basically 0, or practically. And if you go more negative than that, VD of -2, -3, -5, things are not improving anymore, right? So your ID will be essentially minus IS, which is a very, very small value anyway. Let's see what happens at VD equals 0. If I set VD to 0, then you can see that the first term here will become 1, and therefore the two ones cancel, and ID will be 1. ID will be 0. Okay? So the characteristic curve, whatever it is, it goes through the origin. So what I do is that, let me maybe plot that. For all the negative values, ID is going to be really, really small and very, very close to this horizontal line or axis. And at 0 volts, it just goes through the origin. Now, what about, let's say, a VD of 0.3 volts? Now, if VD is 0.3, then e to the VD over NVT, 0.3 divided by NVT, it's going to be e to the 40 times 0.3, e to the 12. E to the 12 is larger, much, much, much larger than 1 already. So you get a very large number for this portion, and multiplied by IS, if you plug it into your calculator, you get 0.1 microamps. So all of a sudden, from currents on the order of picoamps, we are going to currents on the order of microamps. That's 6 orders of magnitude difference in value. Let's just keep increasing VD a bit more. So 0.4 volts gives you, let's say, 9 microamps. Interesting, right? 0.1 volt difference in voltage gives you almost a factor of 10 increase in, a factor of 100 increase in current. VD of 0.5 gives you ID of 500 microamps. So now you are getting to current ranges that are easily measurable. 0.6 volts gives you 26 milliamps, and a VD of 0.7 volts gives you an ID of 1.4 amps. So if I want to keep drawing this, so let's say this scale, let's say each one of these small divisions is half a milliamp or 1 milliamp, right? So at 0.3 volts, I still don't have anything, so it's basically very close to the axis. It's positive for sure, but I cannot see it on this drawing. So this is 0.3, 0.4, 0.5, 0.6, 0.7. 0.4 volts, again, it's a positive value, I cannot see it. 0.5, it starts to go up. 0.6, it's already beyond this scale, it's somewhere up here. So at 0.5 it's like this, at 0.6 it just shoots up, the current. And then 0.7 I don't even bother. So So this is 0.5, this is 0.6. So at 0.5 I had half a milliamp, 0.6 I have 26 milliamps. It's already off the scales. And 0.7 it's basically much, much larger. And usually at those kinds of voltages, something from outside limits the current. So this is the exponential growth that we are familiar with, from your high school physics or from the pandemic that we're going through. The exponential growth is right there. Just a tiny, tiny change at the input makes a huge change at the output. Now, this relationship, amazingly, is valid for 7, 8 orders of magnitude variations in current. It's one of those, nonlinear relationships that is holding up to a lot of change in ID values, amazingly. So this diode at the end of the story, this PN junction, is behaving interestingly. It looks like that, once it is on, once you start to conduct current through it, almost any current can go through it without too much change in voltage. And when it is off, when the voltage across it is negative, there's almost no current through it. Remember that IS 1 picoamp, I should never be able to see it on that scale. So for negative voltages, I don't get any current through this guy practically. And for large enough positive voltages, I get a lot of current through this device. It looks like it's an ideal diode whose characteristic curve is shifted to the right a little bit. How much? 0.6, 0.5, 0.7 volts, depending on the type of the diode that you're dealing with. For a big power electronic diode, it's probably 0.4, 0.5 volts. For a tiny diode on the chip, it's probably 0.7, 0.8 volts. It's actually larger for smaller diodes. But once you're past that knee, once you're past that exponential, that exponential growth point, you almost have a basically unlimited allowance for current. Any current can flow through this device without much change in the voltage drop. It's an ideal diode, looks like an ideal diode whose characteristic curve is shifted to the right and maybe a tiny bit up. So what we're going to do is that, unlike an ideal diode, we can make these things. And we can make millions and billions of them on a chip. As a rule of thumb, just remember that for a typical diode with an N on 1, every 60 millivolt increase in VD, when the diode is on, multiplies the current by a factor of 10, increases the current value by a factor of 10. So if you go from 0.6 to 0.606, from 0.6 to 0.66, the current goes up by a factor of 10. So this exponential growth is what is giving us that knee-like behavior, that shifted ideal diode-like behavior. So I went through some example here to calculate the values. You have some examples on your slides for 3 different diodes, different I's and IS's and N values. Just do a calculation for the current through those diodes and just get a feeling of how these numbers look like. Now, one simplification that we can make here, so remember that ID is given by this expression, IS e to the VD over NVT minus 1. And NVT is a number around, let's say, 25 to 50 millivolts, depending on whether N is 1 or 2. At room temperature, NVT, right, is 25 to 50 millivolts, in that range, right? So let's see what happens when we compare VD to this, right? So if VD is much smaller than, let's say, 0 or negative NBT. So let's say it's minus 1, minus 2, minus 3, right? If that's the case, then the first term here, this term, will be e to the minus, let's say, if it is minus 1, it's going to be e to the minus 20, e to the minus 40, e to the minus 30, something like that. So that term will be very close to 0. And you can show that ID is essentially equal to IS minus IS. Basically, the current is flowing, if this is your diode, you will have a tiny, tiny current going back into the diode. This is not our ideal diode that would not allow any current to go in the opposite direction. But that current is really small. You're talking about picoamps and femtoamps and nanoamps, right? So in most cases, your typical lab equipment cannot even measure that current. So I can say that this is practically zero, right? Practically, when I have a negative voltage applied to the diode, it's the current through it is zero. If VD, on the other hand, is larger than or much larger than NVT, and I'm going to compare it to NVT because you're normalizing, in that exponent you're normalizing VD by NVT. If VD is much larger than NVT, let's say it's 5 times NVT, if it is 0.2 volts, 0.3 volts, right? If that fraction VD over NVT is a large number, a large positive number, 5, 10, 20, something like that, then that first term in that equation becomes much, much larger than 1. You can ignore 1 and simplify that equation. So ID will be IS e to the VD over NVT, or you can write it when the diode is conducting current, when the diode is on, you can say that VD is given by this expression, NVT natural log of ID over IS. Okay? So if the diode is conducting, if the diode is on, you can calculate the voltage drop across the diode from that equation, or the current through it as shown over there. And these are the two equations that I will, or two operating regions for a PN junction diode that I will consider. It's either on, conducting current, forward biased, all of them are the same thing, where I can calculate the voltage drop across it through that logarithmic relationship or the exponential relationship, or it is off, the voltage drop across it is negative, and in that case the current through it is essentially zero, practically zero. It's not zero, but it's practically zero, and I can assume that it is an open circuit. So I either have a device that has an exponential or logarithmic relationship between its voltage and current when it is on, or an open circuit when it is off. So I call this on, off, and this is on, right? And the differentiator is the amount of current through the diode. It depends on your application. If what you can measure is 1 milliamp at minimum, maybe 10 microamp is your zero. So and then if you can measure down to picoamp range, maybe femtoamp is your zero. But on means that you're letting a considerable amount of current to go through your diode. Off means that you are not measuring any current through the diode. It may be there, but it's just so small that it's of little value or importance to you. And that's that for the semiconductor PN junctions. So we have a device that looks like an ideal diode whose characteristic curve is shifted a little bit to the right. There's a little bit of curvature to it instead of the abrupt change from short circuit to open circuit. This is a more gradual change. But nonetheless, the change is so sharp and so fast that we can use it as a diode, or something similar to a diode. And now from the next topic, the next recording, what we're going to do is that we're going to solve circuits that have diodes in them, semiconductor PN junctions in them.